Hello and welcome, everybody. My name is Steve Teresi. I'm the VP of Tech Services here at JL Audio. We have a new guy. This is Matt Mergenthal. He actually just recently joined the training team, but he's been part of the JL Audio family for quite some time now. He's worked in our R&D department doing a bunch of really cool stuff over there. He's really good with a lot of this stuff, and we brought him over to the training side to kind of help me look a little bit better. That ain't working. So Matt, why don't you go say hello to everybody?
Hi, everybody. Thanks for joining.
Fantastic. And the man from the far West Coast is Mr. Rob Haynes. He's our producer and monitor of our chat today. Please say hello, Rob.
Hey, everyone. Thanks for joining.
And the man of the hour is none other than Mr. Nick Ames, joining from our Phoenix location. He's got some special stuff for us. Please say hello, Nick.
Hello, Nick.
Very good. He's been working with us for a while now, huh? So today, I think we're just going to focus on the left and right mid bass, matching that to the subwoofer, and just lather, rinse, and repeat. Continue doing that all the way up the scale for as many drivers as you have in your system. And once you know how to do this, you'll see that it's actually pretty quick and easy.
Probably the first thing to do from here moving forward would be to align all the speakers in time. What I would do is zoom in on the first speaker. And anyway, I just need to set my reference delay for my transfer function engine here. So the easiest way for me to do that is to just look at the beginning of the impulse response and right click. And then that sets the reference delay value for wherever I put my cursor on the beginning of that impulse response. So I'll set that back to 0. So you can see here, if I move my cursor over, you can see it's reading right up in here. You'll see the 4.3 milliseconds or so. So you can either type that in, or you could just right click and it'll enter that value. And then what I would do is mute that speaker and go to the next one. And if it's showing up to the right, then it's the next candidate for being the reference. So then that one becomes the new reference. And so that one's ahead. So that one's back even further. So that one's the new candidate for the reference signal. And this
everyone follow what Nick is doing. So what he's doing, he's looking at every single channel and seeing where in time the first signal from each speaker is arriving at the microphone. We're looking for the latest arriving impulse response, and that's going to be our new 0.
Okay, so now I have set my reference delay right here. So now all that means is that I have a point in the impulse response graph that has this number below it, 8.41. That number coincides with the number in the reference delay field. That's our position in time that we're going to view all of the information. And we've set that position in time to coincide with the latest arriving energy. And so now, since we have delay in the DSP, we don't have an ability, like you said, to advance time, but we can delay time. So we go to the latest arriving energy. We set that as our reference point, and then we can unmute them one by one and scoot them over in time until they arrive at this all at that same point right there. So a fast way to do that is to shift and click in tune. So that just enters that delta delay value right down here. So we just go through and unmute them one by one and just shift and click and scoots them over in time. So now they're aligned in time and to the subwoofers, which were in this case the latest ones. So now at this point is when I would probably switch over to the phase response, and then I might take a look at my mid-bass speakers and see how they are comparing to each other.
The red trace on the top is the phase response of this driver. The blue trace on the bottom is what you would see on an RTA.
That's what the phase graph is always showing, is the relative time relationship kind of per hertz of two waveforms. And the two waveforms in question are your reference waveform and your measure waveform.
The reference is when it started and the measure is when it ended. And then go through all electronics, including all the wires, every device that's in the signal path, including the time of flight from the speaker to the microphone. It's capturing all of that. So if there's anything going on in that entire path, it'll be represented by the red trace.
I'll capture this speaker, and then I'll also capture the phase response. And to capture, I'm just pressing the space bar.
There is a button that you could click. It looks like a little camera in the lower right-hand corner of each of the graphs that does the capture as well.
I just want that to be captured so that I can unmute this one and compare it. That's
right.
So I unmuted this other mid-bass speaker, and I see well, it's out of polarity. So up here in the phase graph, I can see that, it's in the same time, and you can tell it's coming in at the same time because of the angle of the phase slope. So for example, this says 1.72. If I take this back to 0, okay, now see the angle of the phase slope of the red one compared to the gray. It's not the same angle anymore.
So adding delay changes the angle of the phase trace.
Yep, I needed that 1.72. Now that 1.72 that we put in, let me put it back in there. 1.72. Okay, so we put that in using the impulse response. We scooted them all over so they were all lined up at the same time as each other. So that got the timing pretty darn close here.
I'd say, but there's something wrong.
Yeah, but it's out of polarity. And so I can just, you can tell that, you'll see why you can see that so easily. See, look, if I flip the polarity, now they're on top of each other. If I flip it back, it looks like they did. So what I'm guessing, let's look at see, they're all at, so whoever wired this, one of the speakers are wired backwards. That's all that. Yeah. Or wait, hang on. Actually, technically, it could also be that in the input mixer, one of these is flipped. No, they're not. Okay. The input signals aren't flipped. So, all right, never mind. I just wanted to say it, because there is one other possibility, right? There's another place where polarity can get inverted. So,
and this kind of goes back to, we're looking at everything between where the signal started at the signal generator on max and going through every piece of electronics, including the software, before going through the driver and out to the microphone.
Yep.
Indulge me. Flip that polarity, please. So when I see this, I'm thinking, wow, that's really cool. Because remember, the goal is to align them in time. And if phase is time, that's pretty darn good. We are really well aligned in time right there. Now, I do see a deviation above 500 hertz to about 900 hertz. There's a change there. Is that something that we should worry about?
Well, maybe. But, what I say maybe, what I mean by that is, what we can do now is, now that they're aligned in polarity and time, we can capture this one as well down here on the bottom and then unmute them both at the same time. And what we ought to have is a nice summation all the way across their bandwidth. The current live data, which is the blue trace, it is higher in level than either of the contributing two traces. So remember, I captured one speaker, then I muted it. I captured the other speaker, then I muted it. Then I played them at the same time. And so now I can see how they interact because I have both of the original speakers' captures on the screen. And so now with they're both unmuted, the combined energy of both of them, the summed response is what we usually refer to it as. The summed response should be higher than either of the two contributing responses. And
if it was an electrical signal for each of the other traces and they summed perfectly, what could we expect that blue trace to be in terms of level above?
6 dB. So you'll get a 6 dB increase in level if the two contributors are at the same frequency response and in the same time. They'll add up.
That would be exactly the same time. And in this case, the red and the gray trace are not exactly the same, but they're really darn close.
Really darn close. Yeah. Yeah. So let's see what we actually do have here. Here's a place where red and gray are pretty close together. So 5.1 or so up there, 5.1 dB. So
in summation is 5.1 dB, just a slight difference off of an ideal perfect electrical summation.
Yeah. So it's somewhere around 6 dB, right? That's what you ought to see, about a 6 dB increase in level if the two contributors are identical.
If you flip the polarity on one of the mid-bass drivers now, we can see what would change with the summation of one that's out of polarity with the other.
Yeah, I'll flip this one back that we changed a second ago.
Do that.
There you go.
No surprise, we're missing a lot of energy because they're canceling each other out in time. And that makes total sense. And it was seeing that in the phase domain and seeing the summation, I think it's helpful.
It is.
Yeah, and standing outside the car here, I can hear that as well. You can hear very different, sounds very different. So this area up here that you asked about a minute ago, let's take a look again at that. So let's see, I guess it was this one.
It was like from 500 to 900. Yeah.
Yep. So right up here at around 900 hertz or so, that's when we're getting close to the noise floor. So I would probably say that really doesn't matter you know. However, you could back a little bit of delay off of this, and that would move that red trace closer to the gray. So if I back a little bit of delay off.
As he does that, remember when he added delay, it increased that angle, and now he's removing it, so he's decreasing it and moving it the other way.
Right. And so, yeah, see, you could try to get it a little closer maybe, but it's really,
It looks like that might be more of a problem with the frequency response, right, Nick?
well, let's take a look at our summed result again. So yeah, maybe, I don't know, whatever, 1.72 or whatever I just had a second ago, 1.20, right? The difference in the summed response is 1.20 probably has a little bit better total summation up here at the top. It's pretty minuscule. I mean, it's not, you wouldn't really be, it's not a make or break situation one way or the other.
The reason why I called it out, Nick, is sometimes when you're looking at the phase traces, they're not always going to be as perfect as what we're looking at here. There may be some oddity. And once you're familiar with looking at the way the phase of drivers interacts, you can start making determinations of what you chase and what you could probably ignore. And in this case, that weirdness up at the top end of this mid-bass driver is something we could probably ignore because everything else is so darn good. You'd be giving up some of the so darn good in favor of a possible maybe.
Yeah, and I mean, the mid bass is going to start handing over to the mid range
right
at that point. And so anyway, yeah, I think that's good right there where it is. I'd probably leave it 1.20.
And when we got them dialed in, then we captured them together as a group because now they're operating as almost like a single channel in terms of the time domain and their response characteristic. So now with these combined mid-bass drivers that are already very well aligned, we're going to try to extend that alignment down to the low frequency where the subwoofer is going to pick up.
So I just have the summed response. I have the summed phase and the orange down here on bottom. That's the summed RTA response of the mid-bass speakers. You can use your plus and minus buttons on your keyboard and it'll scale the y-axis. Y is the up, down, the vertical, right? It'll scale that in or out. So that's the minus key and this is the plus key.
And that's scaling the capture data as well.
Yeah, everything. Yeah, anything that's plotted on that graph is going to get scaled with it.
The level doesn't affect the phase response.
No, not at all. So the next thing I would do, I suppose, is look at the subwoofer or subwoofers if you've got more than one. Anyway, so our impulse response alignment got us pretty close with these two.
Pretty good.
Yeah, that's
so the yellowish curve is the captured pair of mid-bass drivers phase on the top, right? That's that trace. And the red trace is the live data from the subwoofer right now.
Yes. Yep.
Okay.
Yep, exactly. Now this subwoofer has a bit of an unfortunate thing going on where there's this null effect right here, like right at the crossover region. That's kind of a bummer.
Yeah.
Well, let's just see how well the subwoofer sums with the mid-bass speakers. So, okay, so there's the subwoofer and the mid-bass speakers. This notch that we see here, this is not from a grossly misaligned crossover. That's just a function of the sub has that in its response already. And so when you add the mid-bass in, it just adds up. So if I invert the polarity of the subwoofer, I get a much deeper null here. And you can see the phase response shifted to a new position that didn't exist in isolation with just the mid-bass by itself. Let's mute that sub and go back and look at, because that right there, to be quite honest with you, that's not a bad alignment at all.
No, not at all.
So one thing we could do, we could add a little bit of delay to the sub and move this area closer to the mid-bass, and then the area directly below that'll sum stronger, right? But the further we move this to the mid-bass, if we start to separate these out more, then this area directly below that is going to sum less strongly, right?
Okay.
So we could try it. Let's actually do that. So first let's capture it like it is. And this is the sum response. Okay, so first we'll capture it like it is. Now what we'll do is we'll go into the subwoofer amp that I've unmuted, this one down here. and we will add a little bit of delay to move this down just a hair.
Right. So you're delaying the sub to try to get the phase trace to come a little bit closer to the combined mid-bass trace.
Yeah, see, so it did move it closer in this region, and up to here, but it pulled it away down here. So anyway, so now let's unmute our mid basses again, and we can do that right from here. We don't have to switch back over.
The importance of naming your channels.
Yep. And see, yeah, it's really not any different.
Negligible.
It's the same. Yeah. So yeah, honestly, that's about as well aligned as speakers in this particular configuration with these crossover settings and these EQ parameters are going to get. So Steve, you said something about all pass.
I'd love to see if we can, hopefully there's a need for it, but if not, can we force it just so we could show what that does and how that would show up in phase?
I suppose there's a couple ways we could go about doing that. So you could just place an all pass filter on purpose in one of the mid-bass responses. And then that would be like a mimic of sometimes acoustically what you have is here, let me get these other ones up there. So sometimes acoustically what you have is, I think it's the near side? I always forget. One of the two mid-bass speakers sometimes will have an acoustic effect that's like, let's see, 148 hertz. So
because this car doesn't seem to really need one, we're going to fake it. We're going to force it so you can see what it looks like in the phase domain and the resulting summation that you would get if there was an all pass applied.
Sometimes there's a scenario where one speaker will have a wrap in the phase response like this.
Can you toggle the all pass off? So you'll notice the blue trace didn't change at all, but the phase trace, the red trace on the top did, and it looked like where it kind of went off the bottom of the graph and came back to the top. That's what Nick is talking about, a wrap. That wrap has gone away. So the all pass put a wrap in where there was none before.
Yeah.
So when you're looking at phase, if you see a wrap on one channel and you don't see it on the other, you could put it on the one that doesn't have it to make it match the phase of the other channel. The best you could hope for is to match it on the opposite one.
If I capture this phase response and then turn that on, you'll see more easily where it.
There you go.
See, that's what it did. So sometimes what I just induced on purpose electrically, that will be happening acoustically. And so what'll happen sometimes is you'll have this acoustically on one speaker, right? Let me hide that capture. And so now we'll capture this as if that were our real acoustic reality. And then you'll have this on the other side that, see, it doesn't have that effect right here. It doesn't have that.
And you can see that the alignment at those frequencies are about 180 degrees out. So it's almost like a polarity inversion, but over a very narrow range. And when he sums them together, look at that notch right around where that cancellation looks like. Yep. That drop in output is a result of the phase inversion between the left and right driver in this case, right?
Yep. Yeah. So if that were my acoustic reality, then what I could do is on this speaker right here, I could add an equivalent amount of phase shift such that it overlays our other speaker. And then you would have a more ideal summation across its bandwidth instead of having that notch right there. So that's that one. And then so let me come to this. So this speaker here is the live one.
The red trace on the top, right?
Yep. If we were to put an all pass filter in,
so how would you know where to find the all pass? Like, how would you determine that frequency?
You just put your cursor right where, so I'm on the red one, but I'm looking at the vertical cursor and I'm placing it right where the green deviates, where it goes off the bottom and jumps back on the top. So I'm placing it right in the middle of that deviation. Then I look at the frequency readout. It says 149.3. So you could just come right down here and type in 149.3. And then what I would do with the Q is, I'd raise it up just a little bit to where
you see how those traces are now lining up with the green one better on the phase on the top. That's what we're looking for. We want to align them in time as much as possible across that entire region. The closer we align those, the better the summation.
So if I unmute them both at the same time now, that little null goes away. So that would be, the same exact phenomenon occurs when you have all pass behavior that's induced acoustically. Unfortunately, this car doesn't display that.
Doesn't have a problem, so we had to fake it.
But that's precisely one potential use of
One potential use.
But
the next step would be looking at the mid-range drivers to each other, making sure they line up to the mid-bass, then the tweeters relative to each other, making sure they line up to the mid-range. Remember, though, as you go up the range, you don't want to change anything you did on the lower octaves because that'll break some of their interaction. So you only want to make the changes at the higher frequencies then.
Yep.
I'm wondering if we can open it up for some questions.
Great question that just came in from Tim. I had a mid-bass cancellation like your example, but when I apply an all pass on the left mid-bass, the sound stage will shift to the right. What am I doing wrong?
I guess, first of all, we might want a little bit more context. At what frequency range is this effect occurring? How severe is it? And how severe is the magnitude dip that you get when you sum the two? That would be some stuff I would be curious about. But one thing that I've noticed that as well, what you're talking about, not usually at these lower frequencies, but when I've had all pass filters a little higher than that. And sometimes what I'll do is whenever I apply an all pass filter during the analysis portion, like we're doing now, or anything that might be questionable that I'm doing during the analysis portion, while listening, I will bypass it, right? So while listening, I'll bypass it and then turn it back on, bypass it, turn it back on. And if it sounds better one way than the other, then that's the way I leave it. I use the analysis portion as a means of optimizing all of the alignments of all the speakers so that I know that there's not any gross destructive interference going on one speaker to the other. But then the ultimate kind of arbiter of how these things should be set is while I'm listening. Like with subwoofer EQ, a lot of times I'll apply subwoofer EQ, kind of like we did just now, right? To get the subwoofer shape a little bit more textbook-like so that I can more clearly see how it interacts with the mid-bass. I can more clearly see the crossover interaction. But then especially if a lot of the subwoofer EQ that I've done was cutting, while listening, sometimes I'll bypass some or all of the subwoofer EQ. And if I like it better or if the customer likes it better with the sub EQ bypassed, then I'll just leave it that way. So sometimes some of these tools that we use during the analysis portion are just so we can get a better view a better insight into how these things are interacting, but it doesn't mean you always have to leave them all engaged.
Now, one other question for you, Nick. Could you potentially look at the sub equalization and maybe add an EQ band at where that null is and see if you can make it any better?
Yeah, possibly. I like to do those kinds of things in isolation. So here's the subs EQ, and let's grab one of these and just scoot it up. And I might not want to run such a high Q.
I know a couple guys that might be watching that little null might really bother them.
Yeah, well, hopefully what they get out of these are the overall concepts.
Right.
That's how I can do that, not.
Right. So our focus is on obviously aligning the time, and we saw that there was a discrepancy in time, and it showed up as an abnormality, if you could call it that, in the summed response as well. It's not a result of the time issue necessarily. There's some other weird things with the equalization, which does affect phase, right?
Yep.
And you can see that the phase trace is actually closer to the other line than it was before with that change on the EQ.
So I'm going to capture the sub response again, and
we could expect this to sum slightly better as a result of the change in the EQ. And look at that.
And how many dB of output did we gain from that, Nick?
4.38.
Again, 4 dB.
Yeah,
in the transition region. That is massive.
It's at 80 hertz. It's local. 4 dB locally.
That's still a lot of information.
It's a big deal.
Yeah, it's a big deal. So that's, I think, hopefully the takeaway for the audience is that, we showed a polarity inversion and what that does to a phase trace. We showed a change in delay, and we saw what that did to the phase trace. And now we saw an equalizer and what that does to a phase trace. I'd love to see if we have an opportunity to show what an all pass does.
I want to show you guys something else though, real quick. What we did here, do you see this ripple? In fact, here, this is just like an academic curiosity kind of thing. Do you see the ripple in the response, in the phase response right here?
Where it goes down and then comes back up and then goes
Yeah,
down.
yeah, that little ripple. So the orange response, this one, was what we had before we applied Matt's EQ. So remember, EQ shifts the phase, right?
Right.
And a lot of people are afraid of EQ. They think because it has an impact on phase and they think that it's a bad thing. But actually, what we did by applying that EQ is it made that deviation in the acoustic phase less severe. So not only did it flatten or kind of linearize the response of the subwoofer's frequency response, it also made its phase response less, less deviation in the phase. It's more of an ideal phase response than it was before applying that EQ. So the overall point here is just that the fact that EQs shift phase, that's not a negative thing.
Right. It's not a bad thing. It's just a thing.
It's a good thing, actually, because it's the opposite of what the speaker is doing. So yeah, it's a beneficial thing. It would not be good if I, had an EQ that only affected the magnitude and not the phase. That would be less than optimal. Yeah.
Got it.
Well, it depends on what I was using the EQ for, right?
So what you're saying is a lot of times what you see in phase can be directly correlated to what you would see in the frequency response, but not always.
Yeah, that's right. Not always. It depends on whether or not that the phase response is, it's like a strong reflection.
Right.
Then it could be that, that's a non-minimum phase portion of the frequency response or something like that. But generally, the ripples that you see in the phase response, they have a direct correlation to ripples in the frequency response.
Okay.
Awesome. On that note, I'm going to say goodbye. So thank you all for watching, and I'll see you next time.
Thanks, everybody. Thanks for joining.
Yep. Thanks for your time today, Nick. I know you're a busy guy, so it's
Absolutely.
always a treat when you get to hang out with us.
I like it.
All right. See you, everyone.
Bye-bye.